This is EE 619, lecture 15. So we have already seen how to write a module for a hardware, how to write a Verilog code to describe a hardware, and also how to build a test bench so that we can give stimulus to this particular module we have designed, as well as to observe the output. Now, how to put both of these together in a simulation tool, a logic simulator, and run the simulation and verify the results. We have given two tutorials. Tutorials have been uploaded onto MOOCit prepared by the TAs. So you can verify, you can go through that to figure out how to run the simulations to verify your results. Now, quickly tell me, do you think this test bench can be translated into a hardware? Yes. So how would you translate this hash 2000 time point? So basically 2000 picoseconds into hardware. Frequency of? Is the, okay, so 1 upon this is the frequency, but how would you exactly implement a 2000 picosecond delay in digital circuit? Nothing is mentioned about so to generate this 2000 picosecond, it's not like we are relying on a signal, right? We have just written hash 2000. Is the question clear? Yeah. And how would you do an initial block? I mean, it's a block that runs from the beginning of the time, as far as we are concerned, right? I mean, always block we can understand. It is getting triggered anytime something in the sensitivity list changes. So if you are working with a flop, if you had passage of flop in the sensitivity list of an always block, you know it's going to get implemented as a flop, right? That is a particular from a code you have a direct mapping to a hardware. But what comments can you make about the some of the statements in this test bench? So do you think this can be translated into hardware? Right, but how would you control this 2000 picoseconds exactly? Right, and that element delay is going to vary across corners. You don't have much control, right? Similarly, I've written hash 1000 here. How would that get translated into hardware? So it seems, it looks like this test bench cannot be translated into a hardware, right? That is the bottom line. So this is in fact true. Not every Verilog code you write can be translated into a hardware. So the Verilog code again can be broadly classified into something that can be translated into a hardware, or what we called as a synthesizable code, right? And then there are certain Verilog codes that cannot be translated into a hardware, and these are called as non-synthesizable codes. We are very simple people. We don't use very complicated terminology. Right? So where would you use non-synthesizable codes? Test bench, of course. You can also use non-synthesizable codes during modeling purposes. Let's say you have this very complicated digital circuit. You have coded it such that it is actually synthesizable. Let's say you have this design under test. Now to verify the results, you could parallelly create a model for this, right? This is a model. This cannot be translated into hardware, but because this is a model, you simply have to look at the input and output behavior. So that gives you a lot more flexibility in describing the behavior. You're not limited into thinking in terms of flops or logic gates, etc. There are a lot more constraints, a lot more commands that you can use for describing its behavior. So this way, you can use non-synthesizable codes for test bench purposes as well as for modeling purposes. For example, if you have a ring oscillator, right? Now, to describe this as a model is very easy. You simply have to estimate the delay that you are working with. And you can simply put multiple blocks having that delay and connect it in a loop. So you can exactly specify the delay value and then put it into a circuit like this. Okay. So now, given that you have this option of using non-synthesizable codes for verification, that actually gives you a lot more options. For example, let's say you are doing this particular DUT, and you want to verify its results. So let's say it has some data stream, which is a big sequence of ones and zeros. Now, this data stream could be generated from another module, let's say, which has been designed by another designer. Now, you can simply get a file consisting of that data stream, store it in your PC, and then you can access the bits directly from that file. So you have commands like $fopen, $fread, $fwrite, etc. Again, non-synthesizable commands. But this will allow you to open files in your PC, read data, run it as an input to your DUT. Then you can dump the results again into another file using $fwrite. So you have all this flexibility when you are working with these non-synthesizable codes for verification purposes. Now, another a very nice usage of this non-synthesizable code is we talked about finding the activity factor of a particular net based on simulations. So what actually happens is you will feed in the input pattern that you want, either from another module in the test bench or you pick it up from a data file. And then you dump the information about how this node is switching into another file. And this is generally done in a file format called as VCD. That is, I think, value change dump. So these VCD files can then be taken into other tools which can estimate the power for you. So you dump all this information into a file, and then you can estimate the activity factor for different nets based on it. VCD file is just one of the formats. There are other formats also that you can use, such as SAFE, etc. Okay. But so this sort of covers the session on Verilog. Now, when you are coding, it is expected that your design under test is written in a synthesizable fashion. So the first part of the project, which is the compulsory project, doesn't mandate that it has to be synthesizable, but please try for it. The bonus project is to basically make sure that it is synthesizable. So the problem statement remains the same. In the bonus project, you have to ensure that the code you are writing is actually synthesizable and can be translated into hardware. Okay. One more comment I want to make is, test bench, you can't make it. I mean, there is no reason to try and make it synthesizable, right? So when you are writing synthesizable codes, there are certain things that you have to keep in mind. Like, for example, let's say you have an always block, right? Now, within this always block, you can't be using both blocking as well as non-blocking statements. You have to, within one particular always block, you have to stick to one form of assignment, either use blocking or use non-blocking. Now, another scenario is, let's say you have one always block, within which, let's say you are assigning a value for Q as some input. Now, you cannot be assigning a value for this Q from another always block. So if you have a statement like this, right, this basically corresponds to two flops driving the same node. This will get translated as a flop, assuming you have given a edge sensitivity list here. This will get translated to another flop, and you basically have multiple drivers for one node. Right? So this cannot be synthesized directly by the tools. So again, if you have a variable being assigned inside an always block, no other always block should be assigning values to it. You can use the same Q in if condition, case condition, etc. for other always block. But value assignment cannot happen to Q in a different always block. So there are certain things you have to keep in mind when you are coding for something that needs to be translated into hardware. So are there any? Sure. We'll give you access to actually the synthesis tool, right? If you are interested in the bonus project, we'll give you a login for our lab machines, and you will have access to the synthesis tool. And we'll show you, no, Virtuoso is, synthesis tool is Genus. So digital tools, Virtuoso is mostly an analog tool. You have separate tools for digital synthesis and place and routing. So we'll give you access to the synthesis tool, and we'll show you what command you have to run to see if the code is synthesizable or not. And so there are some tricks, some points that you have to keep in mind, like I explained now. And we'll upload a small document with most of these points. Okay. Now, that said, I also have to explain another way of synthesis called as high-level synthesis or HLS. Has anyone heard about this? So if you are doing high-level synthesis, you are basically removing the need for verilog. So you can use C or C++, one of the high-level languages, to describe the behavior of your code. So you will have the behavior described. And along with it, you also have to write a constraint file. And now there are tools that can give you a translated hardware based on these two files together. Now, the advantage, of course, is very obvious. You don't have to get into the nitty-gritties of writing a Verilog code, making sure all the inputs and outputs are correctly defined, wire register data types are saved, etc. Because you'll be working with a higher level of abstraction. And this method is actually getting very popular on FPGA-based implementations, right? But on the other hand, if you are getting into these details, which means you have better control of the design, right? So writing a behavior and a constraint file and giving it to a tool and hoping that it will churn out the right hardware is slightly different from actually writing the code to map to the exact hardware. So tools are getting much better though. So maybe in a couple of years, much like how Verilog to digital flow is very, very established now, this flow is also going to get established, but it has not yet started in the IC design yet. It will probably take a decade or so. Okay, so we can take a minute to see if you have any questions on this. Otherwise, we will move on to our linear dilemma. You can put the same code also on the FPGA. And it will also have the stages are still called as a stage. You have a synthesis stage, you have a place and routing stage, etc. But what happens on the FPGA is, like I said, the resources are already there. So it's a matter of mapping how this code needs to be established, needs to be translated based on the available resources. Whereas if you're doing it for IC, if you have written for 10 flops, you'll have 10 flops. Okay, so if there are no questions, let us get back to, yeah. You have an FPGA and you have the design ready for it. Ah. I didn't follow your question. So you want to avoid purchasing an FPGA, but verify the code using a test bench. Huh. You don't have the FPGA. Yeah. It depends on what you want to do, right? If you simply wanted to check if the system is able to, if your code is fine, then a test bench file is mostly sufficient, right? You can actually run simulations after PNR also if you have the right files for the FPGA, right? But if you actually wanted to implement something and sell it as a product, then you need the hardware. If the idea is only verification of a particular code, then test bench files are sufficient. Is that your question? We can discuss it after class. Okay, so we have so far been assuming that we are working with the PDK, where if a unit NMOS has a resistance R, a unit PMOS has a resistance 2R. Therefore, our reference CMOS inverter was constructed like this. So what is the total capacitance at the output? This was 3C. Capacitance at the input. This is also equal to 3C. Now let me also quickly show you the NAND 2 implementation. What are the sizes? What is the size of the NMOS? This has to be 2 PMOS. Also, what is the capacitance here? This is 2C. Total capacitance here. This is equal to 6C. Now let's say I take a NAND which is sized 1. So this is the unit NAND 2. And I am driving a load given by CL. Can you quickly calculate the fault propagation delay? So I have basically connected a CL here. Let us draw its RC equivalent. So we are looking at the fault propagation delay, which means both the PMOSs are off. So I will draw the circuit first. To see R by 2. And then you have a 6C and a CL. So let me write the full steps first. So the delay is going to be R by 2 into 2C plus R into 6C plus CL. So this gives you 7RC plus R into CL. This is fine? Okay. So now I size our NAND gate by a factor K. So the NAND gate has been upsized and it is still driving a capacitance CL. So what is the fault propagation delay now? This is 7RC plus R by K into CL. Okay. So here we see that there is this portion 7RC, which is basically the time taken by the gate to drive its own capacitance, right? And this is like an overhead that is going to come with any gate. And we see that it is independent of the size of the gate. Okay. And then we have this portion, which is the time taken for the gate to drive the load. And we are able to reduce it if we upsize our gate. So now we were looking at how to model all of this information together. And the conclusion that we had made was delay is a function of the technology. Because if you design a gate in 45 nanometer, implement the same gate in 90 nanometer, it is going to have different delays. So it is a function of the technology you are using. It is a function of the logic topology that you have selected. In a given technology, a NAND gate as well as an inverter are going to have different delays. It is a function of the load that is being driven and is also a function of the sizing. So we were in need of a simpler delay model that would be able to separate out all these dependencies. And then we talked about how two groups independently came up with the same method for delay calculation. So this method is so intuitive that two groups were able to come up with it independently. And this model is called as the linear delay model. So the first part was to separate out the technology information. So we did it by saying that the absolute delay, the absolute, will be a unitless delay into tau. So here D is the unitless delay. And this is the delay of an inverter. What is the delay of an inverter? So if this capacitance is 3C, because it is sized as 2 and 1, what is the delay? 3 RC. So this is basically 3 RC, but for that particular node. So now you can implement the same circuit across all technology nodes. The unitless delay is going to be same. The tau is going to vary. Therefore, you can multiply the unitless delay with tau to find out the delay in every node. Okay. Now the second part is to define this unitless delay. So we say that this delay is equal to, clearly it should have two parts. It should have a part which is related to its own capacitance and another part which is related to the gate sizing and related to the load that is being driven. So this D, I will write it as P plus F, where the P is called as parasitic delay and F is called as stage effort or effort delay. So now, first we will focus on this parasitic delay. So looking at it, what do you think is the parasitic delay for an AND 2? 7 RC, but now we have to make it unitless. So unitless in terms of the inverter delay, right? So it has to be 7 RC by 3 RC, right? But we are going to make a little approximation to make our lives easier. And the clever approximation we are now making is that the internal capacitances can be neglected. Of the device that you are working with. For example, if this is NAND 2, we will now neglect this internal capacitance 2C. Only the output diffusion capacitance will be accounted. So I will explain. So for example, in this NAND circuit, this is our output capacitance, right? It's capacitance due to its own diffusions, right? And we also have an internal capacitance at other nodes other than the output. So we are going to ignore all of the other internal capacitances. Now let me tell you why it is okay to make this assumption, right? The first part is, we already said that we are going to limit the number of inputs to any logic gate to 4 or maximum 5, not more than that. So because of this, the error that you are going to make is going to be limited. We will not make a very large error in making this assumption. And because we have made this assumption, now we don't have to worry about the exact input pattern that is occurring, because that would have determined whether this cap is initially charged or discharged, and that would affect our delay calculation. So now we don't have to worry about how these internal capacitances are changing. Now the third part is, does the delay change with gate sizing if I include the internal capacitance? So from this example, did your delay due to the internal capacitance change with gate sizing? No, right? So for most of the algorithms where you are trying to optimize what gate size you want to use, this is a constant factor. Your parasitic delay is going to be a constant. Now, whether you make a small error in that or you exactly accurately calculate it is going to not affect your algorithm so much. Because if you are taking a derivative to optimize something, this goes to 0. It's a constant, right? So that way, you are still making a small error in the delay value that you are calculating. But that error is mostly okay. For most of the applications, it doesn't affect your final results much. Now, let's say you are working with an application where the accurate calculation of this parasitic delay was important. Feel free to do that as well. The rest of the discussion still remains the same. So you can estimate the exact parasitic delay and use rest of the methods as it is. Okay. So now, what is the parasitic delay for a NAND 2 gate? By RC. So if I ignore this. Okay, so let us calculate. So parasitic delay would be, this is 2 and 2, this is C. Normalized. So to what should I normalize it to? It has to be normalized to 3R. So this is 2. So you can also calculate the parasitic delay just by looking at the output diffusion cap divided by diffusion cap of the inverter with the same drive strength. Or you know that this is independent of the gate sizing. So you can simply look at the output diffusion cap for a unit DUT, for a unit NAND2, and divided it by the diffusion cap of the unit inverter. So now let's quickly calculate how the parasitic capacitance is for NAND2 based on this formula. What is the output diffusion cap? 6C. What is the output diffusion cap of an inverter? Sized unity? 3C. So this gives you 2. Can you calculate it for NAND3? Let's check. What are the sizes? So these are 3, these are 2. What is the total capacitance here? 9C. So this is going to be 9C by 3C equal to 3. What if you had a n input NAND? This will be equal to n. So you will have n such gates here. So all of them would be sized as n. And you would have 2n capacitance from here. So overall it is 2n plus n. The capacitance here is 3nc. So this is 3nc divided by 3c. This will give you n. What about NOR2? When in doubt, sketch out the circuit and so let's see. So size of NMOS is, this is 1 and 1. This is 4 and 4. What is the total capacitance? So this is 6C. So P will be equal to 6C by 3C, which is equal to 2. Okay. So you can do NOR3. Let's actually do NOR3 also immediately. What is for NOR3? So what should be the value of PMOS? These are sized at 6. So the total capacitance is, so you have 3 here, 6 here, total is 9C. So this equals 9C by 3C equal to 3. So now given any logic gate, you can quickly calculate its parasitic delay. Right? So as a homework, you can do this for a NOR N or the N input NOR gate. Figure out. So now we can focus on the second part, which is the stage effort or the effort delay. So we are going to use this case as a reference and we will derive based on this particular equation. So we need to focus on the second part, which is a function of K and CL. So stage effort is now R by K into CL. Is that all, or am I making a mistake? By 3RC, right? I have to divide it with the delay of the unit inverter. So you have 3RC in the denominator. Let me rearrange things. So let's say I have 1 by K CL divided by 3C. 3C is basically the input capacitance of the unit inverter, right? So I can write it as C inverter. Now I am going to replace this parameter K in terms of the input capacitance of the NAND2 gate. So this is the design under test for us now. What is C DUT if I size it at K? So let's say I have a NAND2 sized at 1. I have another NAND2 sized as K. So this is the input capacitance of a unit DUT. This is the input capacitance of the DUT under consideration. What are the values? Let us check if that is right. So these are sized at 2. These are also sized at 2. This is A, B, A and B. So the node A basically sees a total capacitance of 4C. Is this clear? Okay. So for a unit DUT, this is at 4C. If I upsize it by K, what is the capacitance? All of these are 2K. So the capacitance is now going to be 4Kc. So I can write the expression 1 by K, which is what we need here as, I need 1 by K. Can you give me an expression based on these two capacitances? So unit DUT is input capacitance divided by C DUT. So I will replace it here. So C U DUT divided by C DUT into CL by C inverter. But C inverter is again unit inverter. So I will represent that explicitly. I'll rearrange this. And then I have CU DUT divided by CU inverter into CL by C DUT. So this now has two terms. What comment can you make about the first term? Constant for? Can't hear you. Constant for? Yeah. So once you choose a topology, if I say I want a NAND2 gate or a NOM2 gate, this becomes a constant, right? And this is called as logical effort, represented using G. And the second term, which is now a function of the load capacitance and the input capacitance of the given gate, which has been upsized, etc. This is called as the electrical effort. represented using H. So now the stage effort F is equal to G into H, where G is the logical effort and H is the electrical effort. Let us take a quick look at the electrical effort first, then we'll come to the logical effort. So the expression was H was basically CL by C dot, which is the load capacitance, the total load it is driving except for its own diffusion, right? So the total load capacitance it is driving divided by its own input capacitance. So let me quickly give you an example. Let's say I have a unit inverter which is driving M inverters. What is the value for H? You have M such stages. What is the value of H? So we need two values. We need to know what is the input capacitance. So we're talking about this particular inverter. What is the input capacitance? This is 3C. What is the total load capacitance? So that will be 3M into C. Therefore, H is equal to 3MC divided by 3C, which gives you M. Okay. Now let's say I upsized it by K. Now, how does the circuit change? So this inverter has been upsized as K. What is the input capacitance? This becomes 3KC. What happens to the total load? It doesn't change. So the value of H, which is a ratio of two values, is now 3MC divided by 3KC. So this gives you M by K. So is the calculation of electrical effort clear? Okay. So then we can move on to the logical effort. What is the expression for G? Please go back to your notes and tell me. CU DUT by C unit inverter. Or you can also do input capacitance of a given DUT divided by the input cap of the inverter which has the same drive string. So what do you think is the intuition behind having a logical effort? I mean, it comes out of the equation, but does it make any sense intuitively to pair it like this? It relates how the delay is related to the topology. That is correct. But it also tells us that for a given capacitance, so any topology you select is giving you certain output current or a drive strength, which we have represented using R, right? So it has certain drive strength. It is also offering some input capacitance to the previous stage, right? So logical effort is basically telling you the trade-off involved between the two. Inverter is going to offer the minimum capacitance possible because it has only one input. So it will have an input cap of a gate capacitance associated with a PMOS with that of an NMOS, right? So the inverter's input capacitance is going to be minimum. and it is offering certain drive strength. Now, for any other logic gate you take with the same drive strength, that is going to offer a larger input capacitance to the previous stage. So this trade-off comes out very nicely in this logical effort term. Let me give you a particular example to make this clear. So let's say I take two designs, design 1 and design 2. Let's say here I have a NAND gate, and this is driving some very large load. And let's say this load is contributed because we have an inverter which is sized 100 here. Now I have another design where instead of the NAND, I have a NOR, again driving the same load. Okay. So let's call this instance as I1. Let's say this is DUT1 and this is DUT2. Now let's say I am interested in the delay from this node to this node. And in particular, I am interested to see how the DUT's delay is affecting this overall delay. Okay. And for now, you can, of course, there is a change in the logic from here to here. But let's say for now, we are simply interested in the delay. The difference in the logic is not a concern. Now I can write this delay as delay of I1 plus delay of DUT1. And here again, it is delay of I1 plus delay of the DUT2. What is the input capacitance DUT1 is offering? It's a NAND2 sized one. This is 4C. What about this? NOR2 sized one. Let's quickly check. So these are sized at 1. This is sized at 4. So this is A and this is A. What is the input capacitance? 5. So now this is offering 5C. Okay? And both of them have the same resistance R. Okay? Now for the same drive strength, DUT1 and DUT2 are offering different input capacitances. Right? Now let's say I normalized the input capacitances and I were to compare the drive strength that the DUT is offering. So I want to normalize by, let's say I want to change the size of DUT1. This is now offering a capacitance 4C. The DUT2 was offering a capacitance 5C. I'm willing to change this by alpha so that the capacitance here is 4 alpha C. Now I want to make 4 alpha C to be equal to 5C. What should be the value of alpha? Alpha should be equal to 5 by 4. So now I'm going to size this at 5 by 4 and this is still sized at 1. Can you quickly calculate what is the delay? You can ignore the parasitic delay. Assume that the CL is much, much large, that the parasitic delay can be. So can you tell me what is delay of DUT1 and delay of DUT2? Simply use the term CL for this. What is the delay of DUT1? Ignore the parasitic delay. Tell me only the stage delay. Stage effort. So both of these are driving a CL. Let's first do for DUT2 for the NOR2. Delay will be equal to R into CL. Right? Is there a confusion there? What about DUT1? What is the value of R? It will be 4 by 5 R into CL. So now if I take two different gates, so I had a NAND2 and a NOR2, and I made sure their input capacitances are identical, then NAND has a better drive strength. It has a smaller delay. So now there is this trade-off involved between the input capacitance that you are offering versus the drive strength that you are getting. And this trade-off is actually captured in this logical effect. So now if you had two gates, let's say you had a gate A and a gate B, and let's say gate A had a lower logical effort than gate B. Which of these gates would you use in the design, assuming the final logic that is being implemented is same? Yeah, so you should use gate A. One with lesser logical effort is going to give you more bang for the buck. For the same input capacitance, it's going to give you a larger drive strength. So next step is, of course, to quickly calculate the logical effort for multiple gates. Let's say I have a unit inverter. What is the value of G? Yeah. So this will be equal to 1. So inverter is the only gate with logical effort of 1. Any other gate that you choose, any other logic that you're trying to implement with multiple inputs will always have a higher logical delay. Now let's say I have NAND 2. What is the logical effort? So what is the input capacitance for NAND 2? So that is 4C divided by input capacitance of a unit inverter, 3C. So this gives you 4 by 3. Is this clear to everyone? What about NAND 3? What is the input capacitance? What are the sizes? So this is 3 and 2. Input capacitance is 5C divided by inverter's input capacitance 3C. This gives you 5 by 3. So quickly do for an N input NAND. So you will have N stages here. And N PMOS is in the PUN. And you will have N NMOSes here. So what is the size? These are sized at N. So if I look at the capacitance of a given input, how much is that? So you have N from the NC from the NMOS plus a 2C from the PMOS divided by 3C. So this will give you N plus 2 divided by 3. Okay, so now you can quickly calculate for NOR2, NOR3, and a N input NOR. If you have a connection in parallel, so this is about the unconducted shared diffusion, right? And I'm suspecting that you're talking about a case like this, right? So now you have you have two diffusions to share here and a third one here. So now if you have three diffusions to share, you will have to put a contact to make the connection. And if you are putting a contact, then the devices have to be separated because the contact will also take up. So then it cannot be shared. Whereas if you had two PMOSes like this or two NMOSes like this, the in-between node capacitance can be counted once. This is, of course, assuming that in the layout you are sharing the diffusion. So some of this is layout dependent. You have an NMOS here. You have an NMOS here. So even if you have three, so now you have to think about it in terms of layout, right? So let's say this is one NMOS. Let's say this is your second NMOS, N2. And even if you decide to share the diffusion between these two, right, make them overlap. So let's say I overlapped these two diffusions. How would you put a third NMOS such that it can share this diffusion? So you have one more NMOS that you need to connect. And if you are planning to share the diffusion, how would you share these two? Not possible, right? You will have to put a contact. So to put a contact, you will have to spread them. Okay, so in north to what is the value of G? Let's quickly check. So these are size state 1. This is size state 4. So the input capacitance is 5C divided by 3C. This will give you 5 by 3. For NOR 3, you should get 7 by 3. And input NOR should get 2n plus 1 divided by 3. Okay. So a NOR gate has higher logical effort than a NAND gate, which is why given a choice, we prefer a NAND gate than a NOR gate. This is okay. So our delay, the unitless delay is now being expressed as D is equal to P plus GH, where now you know how to calculate the parasitic delay, the logical effort, as well as the electrical effort. Okay. So I started out by saying that our delay is now a function of a lot of these things. So now the technology information is captured in tau. The logic topology will affect your logical effort as well as your parasitic delay. And the load and the sizing information is now captured in the electrical effect. Is okay? So now let me give you a quick calculation to do. So let's say I have an inverter sized at 1. This is driving a NOR 2 gate. This is sized 2. This is driving a NAND 3, sized 4. And this is driving some very large load. And this large load is because of an inverter which is sized at 64. So your CL is basically 64 into 3C. Now I'm interested in calculating the delay from the input till this one. So let me show you how you can do this step by step. So let me call this as I1, I2, and I3. The aim is to calculate the unitless delay for each of these and then simply sum it up so that you have the total delay. So we are going to do it step by step. I will first list down its Cin. Then we will list down the CL, the load that each stage is driving. Once you have Cn and Cl, you can calculate H. It's basically Cl by Cn. Then you can also list out the G and P, and then finally you can calculate the D for each of these stages. Why don't you give it a try? What is the input capacitance of I1? This is equal to 3C. Input capacitance of I2? So I2 is a NOR 2. So I'll start by considering a unit NOR 2 gate. So this is 1. What is the size? 4. So now what is the capacitance? 5C. Now this is sized at 2, which means all of the values will double. So you'll get 10C. I3, you should get 20C. Any doubts on this input capacitance? You have a doubt? Let's quickly check. So first we have to check the input capacitance for a NAND. So these are sized at 3 and these are sized at 2. So if this is A and this is also A, input capacitance for a unit sized NAND 3 is 5C. But our NAND is now sized 4 times. So all of these will get multiplied with 4. And therefore now your capacitance is 12 plus 8, 20C. Or if you know the input capacitance for a unit sized NAND 3, simply multiply it with number 4. That will give you 20C. So once you write the Cin table, CL table is quite easy. This is 10C, this is 20C, and this is 64 into 3C, which is 192 into C. Now H is CL by Cin. So this is 10 by 3. This is 20 by 10. And here you will have 192 by 20, which is roughly 48 by 5, whatever. So any questions on how CL was written? So you don't account for the diffusion capacitance of each gate. You simply look for what load it is driving. The fan out capacitance is what you look for CL. What is the logical effort of an inverter? Logical effort of an inverter? 1. Logical effort of NOR 2. So you said 10 by 3, right? But we said logical effort is independent of sizing. What is the definition of logical effort? So either you deal with unit DUT by unit inverter, or if you're taking the DUT capacitance as it is, then you consider an inverter which has the same drive strength. So if you are looking at NOR 2 size 2, consider an inverter that is also size 2. So now what is the logical effort? This should be 5 by 3. I3. This is also 5 by 3. Parasitic delay of an inverter? 1. Parasitic delay of NOR 2? Does the parasitic delay depend on the gate sizing? It doesn't depend on the gate sizing. So what is the parasitic delay for I2? Output capacitance of a NOR2 gate divided by the output diffusion capacitance of an inverter. So output capacitance of a NOR2 is how much? 6. So 6 by 3, that will give you 2. What about the parasitic delay of a NAND 3? So you can either consider the unit devices or size it to the same drive strength and consider. Which is 6? Very okay. So parasitic delay for I3? It's a NAND 3 gate. So you have the NAND 3 gate right here. What is the total capacitance? So this is 9C. So 9 by 3, this will give you 3. So now you can quickly do D is equal to P plus GH. So you should get 13 by 3 here, 16 by 3, and 19 here. So the total delay of this path, which will be summation of the smaller delays, will give you 28.67. This is okay? So let me give you the next problem to try out. Let's say you are required to drive a very large load. So I'm assuming that you have to drive the input capacitance of an inverter, again sized at 64. So the CL value is now 64 into 3C. And you are allowed to use a unit inverter as the first stage because somebody else is going to have to drive this. And they have told you that they are going to design such that it can drive only a unit inverter. So one possible design choice is to simply have a unit inverter driving this large load. The second design choice, so let me give you all possibilities and you can calculate the delay for all cases, is to have 2 stages sized like this. Or I could have 3 stages driving the same load. And let me give you one more case. So can you calculate the delay for all 4 cases? Second one's output is, the load is still the same. So don't worry about the logical inversion. Assume that you can still correct for the logic at a later stage. But so this is actually a very common problem that we have to do in digital designs. We'll need to route a clock for very long distances. It will see very large capacitances. And you are usually okay with adding as many inverters or buffers in the path as required. So can you calculate the delay for all 4 cases? And then let's see what inferences you can make. And you can also ask me if something about this calculation was not clear. The first one is very easy. We simply have one device. So we can directly do D is equal to P plus G into H. What is the value for P? So this is 1 plus what is the logical effort for inverter? 1 into what is the value of H? So it is 64 into 3C divided by 3C. The load seen is 64 into 3C. The input capacitance is 3C. So that gives you 64. So the delay is 65. So the moment you have two stages, it's simply easier to do it in the form of a table. I1, I2. What is C in for I1? C in. This is 3C. This is 8 into 3C. What is CL? This is 8 into 3C. You can, of course, write it as 24C, but because everything is inverted, the 3C is going to get cancelled. So I'm splitting and writing it as 8 into 3C. And what is the load? 64 into 3C. So what is the value of H? CL by Cn. So here you have 8. 64 by 8. This also gives you 8. What is the logical effort? 1. The parasitic delay is also 1. So D is equal to P plus GH is going to give you 9 and 9. So the capital delay is equal to 18. So the D is 18 here. So now I leave it to you to find out what is the D value for the other two circuits, but I can give you the final answer. Here you will get D equal to 15. And here you should get D equal to, I think, 15 point something. 15.3. So now that you have these results, please think about what inference you can make from these four results. So there are actually two things we can optimize, right? One is the number of stages that you want to include. And two, given a number of stages, how do you want to size each inverter? So we will tackle these problems one at a time. First, we'll figure out what to do when the number of stages is fixed and you want to size them. Then we'll see what is the optimal number of stages you need to drive a particular load. I'll give you one more homework. Now, let's say in this particular case, from this node, I have one more load being connected. Then you can think about, so this is also sized at 2. You can think about how your table and your delay calculation is going to change when there is a branching like this in the path of your interest. Okay, so we can wrap up our class. Thank you.